in the past week. Some companies are getting a little bit anxious in the sense of we see more and more studies related to, we already saw one of Anthropic last time, like what do people expect that AI will deliver to them in terms of beneficial effects, but also harmful effects. Well, over the past week, we have also seen other companies doing something similar. This is from a group of researchers at Stanford. They have been looking at the effects of sycophantic behavior, the typical behavior where an AI goes, you're absolutely right, that's a fantastic idea, wow, you're so amazing and smart and no one else has done this before, or maybe 20 people have done this before, or there's many papers, but your twist is something extra. And they did some study in terms of which safety issues companies are trying to remove that effect, but it's hard to remove that because when you train these language models through the mechanism of reinforcement learning with human feedback, obviously humans like the answer more where the agent or the LLM validates them. And they find, you can read the full paper that has been published if you're interested in this, but they find some interesting effects that have to do with the fact that, well, even given the fact that users are actually perfectly aware that these models are flattering them and express this sycophantic behavior, but even though they are aware of this and they know that the model is flattering them and is kind of trying to lick the user's boots and so on, still at the end of the day it made the users more self-centered, more morally dogmatic. So it still has effects even although you're aware of what the agent is or the LLM is trying to do there. So at the end you still become less emphatic, you become more convinced that you're always right, even though you know that you're talking with a very agreeable AI. So we do need to be a bit careful in terms of how we interact with these things. Our brain apparently has some, it's easy to be fooled by that or has some inherent loophole there. This comes from DeepMind, so from the Google researchers, and they also have conducted studies where they used over more than 10,000 participants to kind of see how AI can be utilized to influence decision-making processes of humans. And also here you can read the full paper/blog post if you're interested. But here what they find, or one of their main findings, is that it heavily depends on the context that you want to manipulate in. So they tested this, for instance, in a financial setting, where they try to push an AI to manipulate people to maybe make, well, not so smart investment decisions or to go chasing the latest cryptocurrency instead of something that might be a bit more robust. And similarly for healthcare, where also they tested out users conversing with an LLM and the LLM trying to maybe be harmful in the sense of health information that they were providing. And they found that in some cases that worked better than others, revealing that in some settings or in some of these contexts, the guardrails that are already in place on top of these language models worked quite well. Whereas in other cases, they worked less well, and also users were more or less easier to convince. So for healthcare, apparently there, the guardrails already worked better, and also users are a little bit more anxious, let's say, to maybe not believe everything that the agent or the LLM is telling them. For the financial use case, there they found that there is still work to do. So there they still found cases where the LLMs did express harmful behavior and they could be used to manipulate users into making decisions that are perhaps not so good for them. So also a pretty interesting piece of work. Also this I found very nice to see. I remember from a couple of years ago where AutoML was kind of heralded as the big new thing, where you just load in your data set, tabular data set, but okay, fine, into something like an H2O or into something like a RapidMiner, and the tool basically said, well, we're going to run every possible algorithm, supervised algorithm under the sun, and using the largest hyperparameter grid that you can imagine, and then you throw some smart Bayesian optimization on top of that so that you do not need to do an enormous grid search, but you try to kind of navigate through that configuration space a bit more cleverly. And then at the end, you have the best model on that particular data set that you have. And already at the time, people were getting worried and saying, well, why do we still need data scientists if now these things are good enough that they can basically throw everything on top of that? And Forrester and these typical quadrant companies like Gartner, they did a whole analysis on AutoML, and these are the challengers and the typical kind of bullshit. And this article basically looks at, well, AutoML, what is it today? If you look at AutoML, all these companies, they're either dead or they didn't go that far. Also because the fact that nowadays, if you think about AutoML, for most of us, that just means I will ask ChatGPT to write a code for me, and it will probably make good decisions. And probably that thing will even be capable to recommend me good decisions that have to do with pre-processing of my data and feature engineering of my data, which these AutoML tools typically could not. So, okay, that was to be expected. When we thought back then, we also said, well, AutoML, we're not so scared of that because the modeling part, if you go back to that process, that CRISP-DM process, the modeling part, yeah, that's fun, but it's not the most important part. It's what happens before and also especially what happens afterwards. And this article also goes in some use cases where now people are playing with these AI models to do the ML for them, and that's kind of AutoML 2.0, but still what you find if you look at real cases in practice, that same as before, these things do not drive value, no matter how you construct your model, even if it's perfectly automated construction that you utilize somehow. If you can't deploy those models, again, there is that story again, then they will not be utilized, they will not deliver you any value. So interesting to see how these same stories pop back up. It's a nice article. It's nice to see. This, well, no one wants to talk about COVID anymore, obviously, but it's still interesting. This comes from the engineering team at Airbnb, which Airbnb is an interesting company, especially their engineering team is, because over the years they have actually been releasing all sorts of very interesting models, applications. Their engineering blog is fantastic to read through. And here they go into detail about, well, you can build any sort of model that you want, right? We also discussed this. If a sudden shock happens, something like a COVID, all your prediction models, all your time series models, they basically completely break down. If you don't have any monitoring in place, it might be hard to catch. Luckily, they have that, so they did observe that data drifts start to happen. Obviously, you don't need to have a lot of monitoring. In the case of COVID, you know that the world is in peril, so you can basically know that all of your models won't do well anymore. But then they said, okay, given that these models, that they are not capable to detect or adapt to these kinds of structural shifts, in this case, it went even beyond some numbers changing or some distributions of the underlying data changing. It's the whole structure of the data that's changing. And what is especially interesting is what they find is, well, okay, fine, there is a shock that happens during the pandemic itself, and you can basically assume that models will suffer from that, but you might kind of hope to see, okay, in this case at least, after everything has settled down, probably these structural shifts that were happening during the pandemic, that they would return to a normal area afterwards. And that's not what they find. What they found is, well, even after people started to travel again and started to book rooms again, some structural patterns remained in that underlying data that still caused these previous models that we had that would still have caused them to perform badly, right? And that's already a bit more interesting. You might say, okay, during this COVID pandemic, let's not use these models that we have, but maybe a couple of years later, we can just take them out of the box again, same features, same model, maybe it will just continue to work quite well. And they find the opposite of that. But the next question, what they asked is, well, in that case, would it be possible that we can kind of construct some sort of model that at least is more robust against these kinds of structural shifts? And they developed that, and they call that series of models BDARMA. Especially at Airbnb, they like to come up with like their own versions of regression models and so on. But there are a couple of interesting things in there. What you oftentimes see, and especially nowadays when people talk about making models more robust, very often that involves also having some aspect of certainty or uncertainty in there as well. And Bayesian models is one way to do that. There are some other ways as well, but where you're not just want to know like what's the prediction that you're giving me, but also what's your certainty about that prediction. Pretty interesting case to read through, some very informative stuff in there. So still nice to see that they are like experimenting with that and that they're thinking about these cases in practice. This is a quite technical article, but maybe for assignment number 3, who knows? This is an article that highlights one particular library that some people are using to set up agentic loops, for instance, or to set up retrieval augmented generation contexts or chain of thought reasoning. Basically, all of these things have to do with the engineering of a large language model. Like, you know that you have access to the ChatGPT API from OpenAI, but now you want to integrate that in a more larger product where you want to use this thing to first maybe do some sort of entity extraction, and then there is a second prompt that you have where it maybe needs to group these entities together or link them together in some way, and then oops, tomorrow or the day afterwards you don't want to use OpenAI anymore, but you want to switch to Claude instead because you have heard that that's a better model. So suddenly the library that you're using doesn't work anymore because it uses a completely different scheme, and you need to switch that to whatever Claude expects to utilize. Under the hood, they're all just LLM models, but basically the scaffolding on top of that sometimes looks different depending on which library that you want to use. And DSPI is something that puts itself on top of that, and basically the claim is, well, we make it easy to set these sort of LLM-driven processes that you might want to build, right, for data extraction, preparation, maybe setting up products with an LLM in them, and so on. And in an agnostic manner, where also later it is relatively easy for you to switch to whatever provider that you want to utilize without having to rewrite all of your code. And so looks like a fantastic tool, and this article then says, so why aren't you using it? Or why aren't many people using it? And basically it goes through a normal kind of development cycle, a mini case in terms of a couple of steps where it goes, okay, first you do this, and then you realize that you need to add a second prompt, and then the day after you realize that you need to do this, and the day after you realize that you need to do that, and suddenly you end up with a whole bunch of code that's become harder to maintain, where it's difficult to switch to another provider. And if you would actually have used this library, actually the code that you need to write, it almost looks a bit like PyTorch code with kind of this forward definition that you need to provide, but it's basically running this on top of a provider, and it's very easy to switch out providers in this case, and the code itself is also relatively easy, and you don't need to do any kind of special things. So basically it says, well, the end conclusion is, well, people don't like to use it because there is an initial bit of a learning curve there, which makes it hard to immediately hit the ground running, let's say, and start playing with an LLM. But if you do spend the time to figure it out a bit, you can build basically tools and software and products that are more robust, and where you also get a lot of benefits in terms of you as the programmer, let's say, to not have to do that much work. So it's a very interesting tool. There are others as well, like DSPI, that help you to set up these engineering patterns or architectural patterns with LLMs. This is one of them. LangChain, for instance, is another, which is perhaps even more verbose, way more than DSPI is. But interesting, and it's an interesting tool if you want to get serious with agentic workflows and LLM workflows, how to set that up. So also read through that if you would be interesting. Don't read all of this. You can check out the slides afterwards. This is basically two things to emphasize. We'll talk about text models, and one of the things that we'll talk about is the fact that that backbone, that transformer model, as we will see it, that it hasn't changed a lot in terms of, well, the basic architecture hasn't changed for the past years. Still, all the big AI labs, when they develop a new LLM, it's still built on top of that transformer architecture, but they're of course pushing it heavily in terms of making either the attention mechanism more linear, better scalable, or they're pushing it in terms of trying to quantize the weights of a model. And quantization basically means if every weight normally needs 32 bits and you have 8 billion weights, well, that already becomes quite large. Do we need so much precision for each of those weights, right? What if we do it in 8 bits instead? What if we do it in 4 bits instead? What if we do it in 2 bits, right? And you're really pushing it at a limit, then your your different weights that you can express is not that high anymore. Obviously, you only have 2 bits. I mean, you can have 0, -1, +1, and maybe something else in there, but that's it. Is it possible to quantize in such a way that your model still retains its predictive power? And there are already a lot of users on Hugging Face and so on that are very good at this and can minify, you could say, or make smaller versions of models that are just as capable but can run on commodity hardware. But that quantization so far is always, well, it's not in every case perfect. In some cases, the quantization doesn't happen that well, or you can't apply it on every layer, or you need to pick the same quantization effort for all of the layers, or there is some performance loss. So this is TurboQuant from Google research, who introduces a new method for quantization, which they claim works better, does not sacrifice performance, has profound implications, and so on, where they avoid some of the overhead that typical quantization has, and so on. So interesting to see that this is how these companies are trying to make these models actually scale and not waste so many dollars in terms of energy and compute cost. So the quantization is one of the ways forward. Mixture of experts is another kind of pattern that you see, where, okay, these models, they are becoming extremely large, 397 billion. There was a leak coming from Anthropic where they're planning to release 2 new versions of their model as well, and where the rumor already said that we are passing the 1,000 billion parameter threshold. So yeah, they're still growing in terms of size. But yeah, as these models grow, their inference becomes quite slow. So more and more what you see is that to run a certain completion or a generation of an input prompt, that they do not activate all of those weights in all of their layers. The network tries to route relatively intelligently your prompt through a certain bunch of its layers only, but not through all of them. So you don't need to calculate all of the activations in all that 800 or 300 or whatever billion parameter space. And so also that's called mixture of experts, because your model is kind of like an ensemble in that case of experts. For a prompt, you do not activate the full model, you only try to activate as few of the weights as you need, or a part of the weight. So the A17 here, for instance, and others do the, not only Qwen, but others do that as well, basically says, well, the full model is 397 billion weights, but if you use it for to complete a certain prompt or to answer a question, it only activates 17 billion of its weights. And that's something that you can still run on commodity hardware. And this Flash MOE thing takes it a step further and claims that, well, this huge model that you have here, you can basically do that on an SSD that you have. On a standard Mac, you don't need anything special. So people are still trying to push, we want to use large models, but on a normal Mac or a normal desktop computer with an NVIDIA GPU in it, and run it on those things, which is, I mean, pretty impressive that that's still possible to do. And yeah, this is the last one. You have already heard about this. OpenAI has stopped providing the Sora video generator. So now we have to do with, what is it called, Grok Imagine, and with the models from ByteDance, Seedance, and so on. The Chinese models are getting quite good at video generation as well. Yeah, a bit strange, because Disney agreed to invest $1 billion in that thing, to basically say, okay, we can't avoid copyright issues, so I guess that you pay us for that and we invest in you. That's how these kind of things seems to go nowadays, kind of a cyclic investment story for these US companies. But apparently, under the hood, Sora was burning $15 million per day for OpenAI. And where the lifetime revenue was way less than what the costs were per day. So then, yeah, OpenAI, you see that now they're getting serious about becoming profitable, so they start sunsetting some apps. They have also announced that they will try to merge different apps together instead of making lots of different tiny apps. So you can see the first kind of ideas of revising and becoming a bit more serious about what do we keep and what do we kick out. It's pretty clear for OpenAI that they will start focusing more on the agentic workflows and the coding workflows going forward. And potentially the same for Anthropic. Okay. Good. That being said, where is my, yep. So unsupervised learning, we go back to our standard story. So supervised versus unsupervised, we have already spoken a lot about supervised learning. We already have spoken in some cases about unsupervised learning as well. When we spoke about image generation, for instance, in many cases, like when we utilized this variational autoencoder, for instance, that was unsupervised because the only thing that we needed to have is a bunch of cat images, for instance. So they didn't have a specific label. If you then went to workflows where you also want to provide that thing with a text prompt to kind of drive the generation, of course, then the training is again more supervised, because then during the training, you're not just, well, asking it in terms of how good are you at matching the input set of images that you have here, but also how close are you to matching this text prompt that the user has given. And if you talk about it, it already reveals a bit of a story in the sense that this line that we try to draw between supervised learning and unsupervised learning, what's in a name, right? Because remember last time we saw also, for instance, diffusion models, but they are unsupervised because you could say I start from a bunch of images that all belong to the same category, but what do you do with them? You add noise to them, and then you train a model to remove that noise. Yeah, that model is still supervised, right? You still define some sort of loss on that, and you still basically train your model on top of that loss that you extract. So there is still a target, the noise that I need to remove. Same for an LLM. Yeah, you start with a whole bunch of text that you have gathered from the internet. There aren't any specific labels there, but you kind of make up some task, right? Okay, given a bunch of text, can you predict me what comes afterwards? So very often we call these kind of tasks self-supervised. Like, okay, you don't have a clear label upfront in mind that really comes from a specific task that you have, but given the data that you have, you try to extract some supervised task, remove the noise, or try to generate me an image that looks like those images, for instance. And then another model, a discriminator that tries to detect whether it's a fake or it's a real one. Or in the case of a language model, predict me the text that comes afterwards. So what really is unsupervised, yeah, you can argue about that. Even for some of the dimensionality reduction techniques that we will discuss, they are unsupervised because, again, we don't have a clear label that we want to stick in. But if you look a bit closer, you could also argue that, yeah, but they optimize something. They also reduce some sort of error or loss. So again, isn't that some kind of supervised task as well in that case? So don't really see this as black and white in the sense that you either have this or you have that. Some people will also describe this as well. In the first case, you want to do prediction, but we have seen, well, not always, sometimes you want to do generation of things as well, and you use the same kind of models. Unsupervised techniques, they're more used in a descriptive setting, but also not always, because very often you use unsupervised techniques like clustering, maybe in a pre-processing pipeline, on top of which there will still be a supervised learner. So it's a bit annoying to kind of try to squeeze the techniques that we have in either this or that. Take a bit of an open view in terms that you see many of the techniques in unsupervised learning that they also reduce or some kind of loss or some error or optimize something, or the techniques from unsupervised learning, they show up in larger pipelines where the end goal is still something supervised. But okay, to keep it simple, at least we could say in the unsupervised setting that there isn't, like in the sense of tabular data, a clear column for which we can say that's our target, right? So that's the price that I want to predict, or this is the binary target that I have here that I have constructed. So we don't assume that we have that available. It might still be that we do have it, and then we have two choices for that target column. Either we just consider it to be another feature and we bring it in the unsupervised learner, right? But then it will be harder to utilize this in a kind of predictive pipeline because you don't know what the targets will be in the future. But if it's more for descriptive purposes, you could do that. Or you could say, well, I kick out the target and I will just do this based on the features that I have instead. So the most common case, and I think I already mentioned this in the first week, very often what you do see with supervised models is that the kind of general goal is, okay, given a feature vector, predict me an outcome and construct a model for that. And so the task is always the same there, but the differences lie in the way how these models worked, right? Some are more linear, some are more parametric, some are more data-driven. We have seen the differences between discriminative versus generative models, where either you try to map the features to Y and you learn some sort of decision boundary, or you do try to learn a full distribution on your data, where we say, okay, given the label, what's the distribution that maps to the features? In the case of unsupervised techniques, there the general goal is about, I want to find a summarization of patterns that are present in this data set. And there the models differ or oftentimes get categorized in the sense of, okay, but those patterns that you want to find, what should they look like? What kind of patterns do you want to look for? Is that a grouping of things, in the case of clustering, for instance? Is that things that appear frequently together in your data set, and you're talking about association rule mining or frequent item set mining, for instance? Has that more to do with, I want to just reduce this high dimensional feature space because I have 100 features to something smaller? And that's kind of a summary view, a summary pattern that I'm looking for. Okay, then you're doing dimensionality reduction, right? And then you can argue about what is a good reduction of that feature space. What do you want to retain? Which sort of distances that are present in the original feature space do you want to remain present in the reduced feature space, as we will see? Then that is your pattern. Or in the case of anomaly detection, there you're saying, well, I'm looking for things that stand out, that are anomalous, that are weird, that do not happen a lot. So rather than the frequent things, I'm more looking for the infrequent things, or I'm more looking for the outliers that are present in my data set. But maybe going beyond the typical z-score and histogram stuff, as we saw it in the pre-processing case, but also more from a multivariate perspective, right? Where it might be that if I only look at one feature that I don't see any outliers, but only after combining how things appear together and those interactions, that then the outliers start to stand out. So how do I do that? So those, in the case of unsupervised learning, you could say, okay, the models that we have differ in the sense of which pattern that you want to look for. So clustering is then the first one, and there the pattern is, okay, I would like to group my instances together. I would like to construct clusters over my instances, and obviously already with some kind of assumption in mind, if I make such a clustering, and I look at two entities, two instances that you have placed in the same group or cluster, I expect them to be similar to each other in some way. And you could discuss about what being similar means to you, right? But I do expect that things that you put in the same group, that they are similar in some sense. And if I compare two instances coming from different groups, right, or I compare groups as a whole with one another, then I expect those to be dissimilar, right? So the inter-cluster similarity should be high, and the intra-cluster similarity should be low. So sometimes this is the goal in itself. If you want to do some sort of customer segmentation, makes sense that you group your customers. Very often you already have some bias in mind in terms of what these groups should then also look like, or how many groups that you expect to find. But very often these techniques are utilized to get some basic insights in data, and maybe also as a featureization opportunity for a larger predictive pipeline, and that you use this as features. But it's quite subjective, right, this whole story, because even for a simple two-dimensional, so we have two features here, the x-axis and the y-axis, a couple of toy data sets that are plotted here, and I show you some different clustering algorithms, so they are organized in the columns. So this is algorithm 1, algorithm 2, algorithm 3, algorithm 4. Yeah, I guess if I would ask to you, which one has your preference? Who has a preference? Yeah? The third one? Yeah? Others agree, or some people disagree? There's no right answer here. On whatever the algorithm that you utilize, this is the best outcome for the algorithm. But I would tend to agree, and number 3 speaks to us in some way. But it's not that easy, right? So the first row, there you could say, okay, the data is organized in nice convexly shaped blobs, so that will be relatively easy. But humans do look a bit further than just blobs alone, right? We also look for continuity, and we then tend to prefer this solution way more than, for instance, where you also take this blobby approach in this solution. And same here, well, same continuity, but circular-wise, also these kind of non-linear kind of structures, we would like a good clustering technique to catch. Of course, this is an argument that you can easily spot in 2 dimensions. Typically, you work with more. But the question is, okay, what do we expect from a clustering technique for it to make sense to us, right? And indeed, it will be more something like number 3. Now, generally speaking, clustering techniques, they fall into categories. And either you can say that your technique is a hierarchical clustering technique or is a partitional clustering technique. Main difference between both of them is that with a hierarchical clustering technique, you get a full hierarchy over your instances, meaning that stepwise, this thing will tell you how you merge instances together to form groups, and then merge groups together until at the very top you have placed everybody in one single huge group. And you can do that from bottom to top, or you could also take it the other way around, where you say, okay, I start with everybody in one huge group, and I will divide that stepwise to create subgroups until everybody is just a group on its own. So the way how you construct that tree, if you will, or that hierarchy can go bottom up or can go top down. So hence why there you have both agglomerative clustering and divisive clustering. Divisive, there you start with, okay, I put every instance that I have in one single cluster, and I'm going to make cuts. I'm going to make splits and split them up stepwise. And in the agglomerative case, there you start bottom up. You put everybody on their own in a single group, and you merge until you reach the top of the tree. But at the end, you get that full hierarchy, you get that full sequence of steps. So what your final clustering outcome will then look like still depends on where you want to position yourself in that hierarchy, right? At which level you want to position yourself. So that's nice that you have that option there. Also has some drawbacks. Maybe that will be a bit slower, right? That might be why spend the time on building up this whole hierarchy. Will also have some benefits to us, as we will see in a second, where sometimes it might make sense to use hierarchical clustering. Partitional clustering, there, the idea is that a solution, you let a thing run, and you get your clustering solution that might still look different depending on hyperparameters that you set. And very often an important hyperparameter that many of these techniques will ask you to set is how many clusters do you want? Like in the case of k-means, the k stands for how many clusters would you like to get at the end. Some don't even ask that and will just do that on their own, right? Some are more configurable with other hyperparameters as well, but they all are similar in the sense that at the end, when they're finished, you get your cluster solution. And you don't get that full hierarchy to navigate over, you just get the solution that's there. You can pick another solution by changing the hyperparameters or the data, obviously, but you just get the solution out of there. So this is this hierarchical clustering. So agglomerative, easy to see. You go left to right. Everybody starts in their own cluster and you build up the whole bubble. Divisive, you start right to left. Everybody in a single cluster and you make splits. Now, maybe if you look at this, you might have a couple of questions. So you might say, well, why do both exist? Isn't it the case that if I have an agglomerative technique and I have a divisive technique and I let both of them run, that I would get the same hierarchy? Well, no, right? Well, maybe because you use different similarity metrics. Well, no, even if you use the same similarity metric. The reason being that in both cases, either if you go left to right or right to left, that these choices that you make, kind of like our decision tree from way back when, that this is greedy, right? At every step, you make the locally best choice, right? But you never backtrack on your choices. So that's why if you start from the top or you start at the bottom, that you might get a different outcome. Weirdly enough, you could almost say that a decision tree kind of builds up some divisive structure in that sense, driven, of course, by a supervised error function. In this case, well, same, you can kind of feel that, okay, also here, if I need to make a choice, in the case of working agglomeratively, the choice will boil down to what is the best pair of existing clusters, right? So even in the initial case, even though everybody is in their own cluster, I do have clusters. What is the best pair of clusters to merge in this step? So that's the decision we need to make in the agglomerative case. In the divisive case, you will notice there that it's a little bit more tricky, right? Because there, not only is the question, okay, let's say I'm in step number 1 here, and I have C, 3, 4, and 5 in one cluster, and so 1 and 2 are in another cluster, right? But there, the question I need to make, okay, not only which existing cluster will I pick to split, but also given that existing cluster, how do I split it into 2 pieces? Right? So even if I would have decided I'm going to pick this one, right, and I will split this one up, well, how? C3 and C4 on its own, C3 on its own, C3 and C5 on its own, or where will I put that split? How will I split this cluster up into 2? And if you think a bit about it, about the number of pairs that you need to evaluate, or number of clusters times number of possible splits per cluster, where do you think you would have to evaluate the most candidates? Would that be in the agglomerative case, or would that be in the divisive case? Just based on intuition, let's say you have 100 instances and you're somewhere in the middle, you have already created 20 clusters. what's easiest? Going over all the pairs and seeing which one is best to merge, or going over all the clusters, all the splits per cluster, and seeing which split is the best? Any gut feeling? What would require most evaluations to run over? Well, the divisive case turns out to be much harder, right? Even if I give you already, okay, we decide a cluster, but it has 20 instances in it, the number of potential splits that you can make already quickly explodes compared to, okay, we have 20 clusters and we need to go over all the pairs, but at least the pairs are ordered, right? So cluster 1 and 2 and 2 and 1, probably or hopefully they give me the same metric. So that will be way less evaluations. So agglomerative is way more computationally efficient than divisive will be, right? So that's typically what we'll go for. Which is weird, because if you compare that to our decision tree, which worked divisively, right? But still there it was a bit different. There we did the same operation per leaf node anyway. We didn't first select the best leaf node, and then per leaf node we went over all the possible splits in the instances that were in that leaf node. No, there the possible splits were driven by the features that we had and the splitting points for those features, not by the number of instances in those leaf nodes. Here, it is driven by the number of instances in the clusters, right? So hence why divisive blows up so much in this case. So agglomerative will be the way to go. Okay, let's assume that for a second then. So for agglomerative, I will evaluate every existing pair of clusters, and what I want to kind of figure out, okay, what is the reduction in loss, let's say, or maybe I lose quality by merging this, but then I want to make the merge that gives me, let's say, the least cost in terms of doing that. So obviously, you will feel that it's kind of based on similarity again in some way, right? If I have a bunch of clusters, which two of them will I merge with one another? Probably the one that are closest to one another, right? So in terms of distance that are closest to one another, similarity, the ones that are most similar to one another. Now, that means that we will need to have a distance metric, or we will need to define a similarity metric, and not just between two instances, because we are not merging instances, but between two clusters, things that have a bunch of instances. But even if you would say, okay, between two instances, yeah, you can use your standard similarity metrics as we will see them, but again, this invites us often to think a bit more in terms of from a different perspective, like if I have textual instances, pieces of, or tweets, right, and the tweets are my instances and I want to cluster them together, probably there is a better distance metric that works maybe a bit more better on text than just on numerical data that I would have. If my instances are pictures and I want to merge those together, again, think a bit about what makes two pictures look alike. Kind of similar story as what we saw with our image models, right? You could say, well, just compare every pixel, red, green, blue, calculate the difference between that. Well, then these two pictures will be very similar to one another. Whereas you might say, yeah, but no, one is a human, the other is a dog. So then you might maybe look for things such as perceptual similarity, right? And again, that will then be based on, you know what, how about you push both images through a pre-trained convolutional neural network that you have, and you extract some intermediate activations, and you compare those, because those already work more, remember, in those later layers, on the structure of the image, rather than the texture and the patterns and the edges and so on. So if it's more about structure that you want to have the similarity over, then maybe it's better that you first push those images through a couple of layers in your CNN network that you have, and you calculate the similarity between the output of a layer of CNN units, and that will already work better. So a perceptual similarity that you might use there. So don't think that you're always stuck to Euclidean or Manhattan or cosine distance, the ones that you find in every textbook. Think about the distance metric in terms of the data that you have and what matters to you. But let's say that we have one of these distance metrics. So we do have a simple numerical data set, so we can assume, okay, every instance is a feature vector with numbers in it. Fine. So typically, well, Euclidean distance, right, or squared Euclidean distance, or the Manhattan distance, that's kind of orthogonal, follows like the Manhattan street plan of New York, and follows kind of orthogonal distances over the dimensions that you have, or maximum distance, or many, many more, right? So take your pick. Cosine distance is one that's often preferred if you have very high dimensional vectors and you want to compare those. So that's another one that shows up quite often as well. Now, what we do know, or what we can easily say is, even if you come up with your own idea of a distance metric between two instances in this case, right? So this is still between two instances, that if you ask for the similarity or distance between A and B or B and A, that should be the same, right? We wouldn't expect our metric to give a different result. Well, why not? Yeah, again, it's something that can be argued, right? Because let's say that you are working in a spatial context and you want to use travel distance. The time, for instance, that you need to take to drive from Leuven to Brussels at a certain point of the day might not be the same as from Brussels back to Leuven, right? So that kind of symmetry, maybe that's something that you actually do want to break, and then worthwhile testing out if your clustering technique or any other technique that uses similarity can still work on that. Same for k nearest neighbors, for instance. Also there we saw such a similarity pop up as well. You could also wonder about that symmetry effect there if you would implement that differently in a k nearest neighbor style model and what that would mean in that setting. Maybe what makes a bit more sense, if I ask for the distance between an instance and itself, that distance is 0, right? You're completely self-similar. Hopefully that's something that we can all agree to, that would never be something different than 0. Also, it's easy to make sure that all of our distances are positive, right? Negative distance interactions between humans, that can sometimes happen, but for feature vectors, it's nice that these things are positive. If they're not, add a constant to them, to that distant matrix, and basically fix it that way. And triangular inequality, if I want to travel from A to B, that should always be less than if I have an intermediate point in between, right? So if I go straight from Leuven to Brussels, that distance should always be lower than if I first visit another city on my way, right? So that's also a good property, or a property that many of these distance metrics want to have or need to have. Issue, whatever I pick, right? I can just, in SciPy or scikit-learn, pick from 100 distance metrics. In the case of this agglomerative clustering that we are discussing, remember that we're not really calculating distances between instances. I mean, in the very first step, I can get away with that because every cluster has a single instance. But from the moment that I already put some things in a cluster together, I'm basically calculating distances between clusters of things, not between the instances themselves. So I need something on top of that to make that work. And again, here, in the case of agglomerative clustering, you can pick a couple of things, and they're not that difficult to understand. They're basically quick stop solutions. You can say, well, what you can do to know the distance between two clusters, first calculate the pairwise distances between all of the members that you have. And then the overall distance is just, well, the two instances that are closest to one another. So is the minimum distance. And if you utilize this in the case of agglomerative clustering, you will typically find that this leads to clusters that are longer, more skinnier looking, right? That's kind of an effect that you then get. Maximum also exists, and that's called so single linkage or minimum, maximum linkage or complete linkage. So this is called the linkage criterion that we utilize. This leads to more tighter clusters. Since you're calculating all of these pairwise distances anyway, you might just as well say, well, average them. You have done the work to calculate their pairwise distances, so why not just average them? And indeed, that's favorable in more cases. That's a bit more robust to noise already, so that's what many defaults utilize. And then something what you could also do, if you do want to avoid having all of these pairwise distance computations, you could also say, well, let us first calculate or construct a center point for each of the clusters that we have. And now we need to be a bit careful, because this is one of the benefits that agglomerative clustering easily gives us out of the box. Because calculating a centroid between, for instance, my two-dimensional points here, which are numerical vectors, numerical coordinates, calculating a center there is relatively easy to do. But if these things would not be numerical points, but would be images, or would be pieces of text, tweets, if I give you 5 tweets and I ask you to calculate a centroid for that, that will not be so easy, right? So in that case, it's nice that with agglomerative clustering, you can just, if you do have a distance to calculate the distance between two pieces of text, at least then you can utilize this average linkage criterion without having to bother to also define how you calculate a centroid on those pieces of text. So agglomerative clustering can still be useful in cases where I know the distance between two items. That's something I can do, but I cannot really construct a concept of a center point for my data that I have. If you can, in the case of numerical data, can be helpful, of course, because you need to calculate way less distances then. Also very often, another default what gets utilized is the Ward's linkage criterion. And it basically says, well, the distance between your two clusters now, A and B, is equal to the sum of squared errors in A and B minus the sum of squared errors that you had in the cluster A on its own and the cluster B on its own. Okay, a couple of things here that maybe speak to us or stand out or might be comparable to what we saw previously. This looks somewhat similar to what we were doing with our regression trees. Also there, we said, well, the information game that we utilize there is based on the reduction of the MSE, right? And we said the MSE is calculated in terms of if a leaf node needs to make, or a group needs to make a prediction, that prediction is the average of the targets that we have. And then we calculate the mean squared error by just taking the difference between that average prediction and all of the members in that group. We average over that, and when we do that for the two subgroups that you propose as well, and we look at the reduction that we got there. Does this still reduce that mean squared error that I have there? The thing, what we had with a regression tree, however, is that for every group, there was a prediction that we had, right? That average value for those targets. Another thing that the information gain did, it also weighted the number of members that ended up in the left-hand side and the number of members that ended up in the right-hand side, because we wanted to prefer splits that were more balanced, right? We don't do that in this linkage criterion. So here it's technically fine that you separate off even one member or you merge based on that. So there is no balancing effect in terms of that. So even if you want to merge a cluster that has 100 members with one that is only one, okay, fine, you can do that. That doesn't get penalized in any way. Another thing maybe that's, that we need to kind of resolve is if we see, okay, MSE or SSE in this case, since we do not have a target in any form here, so an average is also not something that we can kind of construct. So how do we calculate SSE when you're talking about a cluster? So before you were talking about a group or a leaf in a decision tree, and there I had all of my members, and there basically I calculated my sum of my squared errors by saying, okay, what's the distance between every member's y, its own target value, right, and this y hat prediction for my members. Also, you could subset this with I as well, because you could say I have a prediction per member, but with the difference here that, okay, in this group, all of these y hats, they are the same. They're just the average value over all of these targets that I have in this group. And that's what I used as my y hat for my decision tree. In the case of a clustering solution, and there, if I have 2 dimensions, you can really, again, see it as coordinates now. This x vector that's associated might not be 2-dimensional, but might have multiple dimensions. Here, to kind of visualize it, I need to do it with 2 to make it easy to understand, at least. So how do we calculate what's the SSE of a cluster? Well, there we say we sum over, not y and y hat, because we don't have that. So we sum instead the distances between every point and, again, a centroid that you define in that cluster. Right? So your centroid is basically your y hat position, if you will, and you sum the distance, or based on the distance between the points in that cluster. So again, here it's based on the sums between every, xi, let's say, and the center point squared. And that's how you calculate the measure of SSE for a clustering solution. Also means that, obviously, something that has a 0 value is if I stick everybody in their own cluster, right, that technically speaking, in terms of SSE, that would be my optimal solution, right? Because then everybody's exactly the same as that single centroid that's in every group. So that would be the best solution. But here I'm merging, right? So basically I'm saying, well, here basically I try to merge based on what is the merger that increases my SSE the least, right? I know that I will increase my SSE. My worst solution is putting everybody in one huge cluster, right? Because then you're all far away from the centroid, right? But I try to avoid the loss of quality as much as possible in that case. Because I'm building upwards, this works. If you would like to do it divisive, you could do something similar, of course, but there you would need to take another approach. There your approach will be, okay, I do need to make a split in some of my existing clusters. Obviously there you will probably pick the split that leads to the biggest improvement in SSE, that lowers your SSE the most, until you end up on the very left-hand side where you have ended up with the situation where your SSE has become 0, right? Because you have put everybody in a singular cluster, or in a singleton cluster. Now, in any case, at the end you obtain this hierarchy, which is nice. You don't need to specify your number of clusters in advance. You can basically position yourself in this hierarchy and decide upon how many clusters that you want. It's nice because you don't need to have this centroid definition. If your instances or pieces of text or images, typically agglomerative clustering works quite well. You still find a local optima. Your cluster hierarchy is not necessarily the best one because you make greedy choices as you build up this hierarchy. You never backtrace any of the decisions that you have made. And obviously, you will need to normalize your features first because every distance metric is sensitive to scaling over your features. If you have a feature that goes from 0 to 5 million and another one 0 to 100, well, your distances will obviously be heavily biased. So you need to normalize your features first. You can also then visualize this hierarchy by means of a dendrogram, right? 2 R's in that. Where you can kind of, basically this is that hierarchy but visualized a bit easier, which stepwise shows you the clusters that it is merging, or stepwise shows you the splits that it has made. Obviously, this can already be, in some cases, an initial way to spot anomalies. Because typically what you will find is that, and this is of course an extreme example, but that instances that are like a bit on their own, that they take a long time before they get merged in to an existing cluster. And sometimes, maybe if 2 people are close to one another, you will see that they are merged pretty quickly as well, but that there is then a long line before the next merger happens. And these long lines then indicate, this subgroup probably is some sort of an anomaly, right? If I pick 3 clusters and I make my cut over here, I will have this group, and then that instance on its own in a single cluster. Now, divisive, I already mentioned, well, you can come up with some criterion based on SSE that could drive your splits as well, very similar to what you used for a decision tree, but not balanced in that case, and also not based on the distance or based on your residuals, let's say, but based on the distance to a centroid that you will then probably have to define. If you cannot define a centroid, divisive clustering will also be a bit nastier to do, but you could set it up. But you will still be limiting the fact that there is a lot more evaluations of potential splits or candidate splits that you will have to make, which is why in most cases, or not to say all of them, that you will not find implementations for divisive clustering, for standard tabular data at least. When we talk about graph learning later on, and we talk about community mining, which is basically clustering on top of graphs, there we will see that some of these techniques are or feel a bit more divisive in nature, but for standard data, it's all agglomerative, in the case of hierarchical clustering. So then what about partitional clustering? Well, here comes our good old k-means friend, discussed in every basic course on analytics, but rarely loved in practice for reasons that I will discuss a bit. It's a simple idea. The idea is, okay, you need to give me k. How many clusters do you want to get at the end? You have your feature space, let's say the blackboard, you initialize k cluster centers. So I pick k starting positions, centroids. So again, we do need a definition of a centroid that I pick on this feature space randomly. And then there is an assignment step followed by a centroid movement step or recalculation step. And that continues to happen in a loop. Assignment means, okay, now that I have my 3 centroids, I need to assign my instances to those centroids. And I'm going to do that based on distance. So if I have an instance over here, which centroid do you belong to? Again, I need a distance metric, Euclidean. You're closest to this centroid, so you belong to that cluster. Then you have an instance over here, you belong to that cluster, you belong to that cluster, and so on. But issue, now we have assigned everybody, but my centroids are not in the right place. So I recalculate my centroids, and so this one needs to move from here to the middle of these guys, over there, right? So you move your centroids. But problem, because I moved my centroids, I need to reassign, potentially. But because I reassigned, I need to move my centroids, but because I moved my centroids, I need to reassign. So this happens continuously. When does this stop? Well, at some point you will see that you are not making reassignments anymore. Everybody stays at the centroid that they were at. Also means that the centroids don't move anymore. So then you can stop. Sometimes it can happen that certain instances continue to jump back and forth and that this thing never converges. Then you can restart and try it again, or just say, well, after 10,000 iterations, I also stop, something like that, right? Or maybe the movements have become so tiny that you can also stop. So there are a couple of stopping conditions that you can implement on top of this thing, but that's the basic idea. So a good cluster solution has high intra-cluster similarity, low inter-cluster similarity. So k-means, what it basically does, it tries to go for optimizing high intra-cluster similarity by optimizing towards a minimal total distortion, meaning that the sum of square distances of points to their cluster centroid, as we have just seen, it tries to minimize that. So again, how do you calculate the SSE of a full clustering solution? We sum over all the clusters that we have. We sum over all the instances of that cluster. We take the distance between where that instance is and its centroid, which is, in the numerical case, the average in that cluster, right? The centroid, you could also say here, and you square that. And you will see over time, as k-means runs, that it iteratively reduces this loss. Iteratively, meaning that likewise, for stochastic gradient descent, the clustering solution that you end up with at the end might not be the optimal one, the globally optimal one. You might get stuck here in a local minimum. So also this is pretty dependent on the lottery ticket phenomenon, on your initialization. Now, what is initialization here is where you placed those weights, right? Interestingly, you could also say, well, I have 3 cluster centroids that I need to place. So basically, if I have an n-dimensional space, then I have a 3 by n weights matrix. And given a piece of data, I can then calculate this loss at the end. I can actually also implement this using stochastic gradient descent in that case. Yeah, why not, right? And you might also get stuck in a local minimum, because also there your weight initialization, where you place your initial centroids, matters as well, so same thing. So what if you get stuck? What if you see, well, this SSE plot over rounds of iteration that I get, it did something like this. So that's there it stopped. Is this now good or bad? Well, restart a couple of times. So a lot of implementations, what they will do under the hood, they will not run k-means 1 time because it's fast enough. They will run it 10 times and they will give you the solution that reached the lowest SSE out of them. Weirdly enough, well, not so weird if you think about it, if your data is one-dimensional, so you're basically clustering on a line, then this is guaranteed to give you the global optimum. So then this always converges to the global optimum. That's a nice tidbit of information, let's say, but there it is possible. So this is easy to implement and debug. It's intuitive. You know what it optimizes. It's relatively efficient. Relatively, I mean, you're moving and assigning and moving and assigning. There can be a lot of work to do if you want to try this out with 1 billion instances, right? But again, it's doable. You can parallelize this in some way as well. Does only work, of course, if we can calculate this mean here. So if we can come up with a centroid concept again. If our data, we have images, then k-means will not work on the images, because what's the center between 2 images? And just calculated the average in pixel space between 2 images. If you have a white image and a black image, the average is gray in that case. So you can come up with a centroid, but it's plausible that it's not a very good concept in that case. yeah, what if you have categorical data? Do I just dumbify it in some way and I use that, but that leads to a lot of features that I have, and then most of them will be either 0, with only one column of them being 1. So that's a very sparse representation. So maybe there you would maybe first use some embedding technique or an autoencoder even, or PCA, and maybe do something there instead, as we saw in pre-processing, to work on that feature vector. So again, the representation here matters in tandem with the distance metric that you want to utilize. Try random restarts, as was already mentioned, or switch to k-means plus. You need to specify k in advance. This is another effect. If you plot the SSE that you end up with in terms of number of clusters, so now not number of rounds of iterations, which typically you don't see, but number of clusters, you can rerun k-means, restart it every time 10 times and try it out for 1 cluster, 2 clusters, 3 clusters, 4 clusters, all the way to 100 clusters. Obviously, same effect. Here your SSE is largest, right? Putting everybody in one group has the largest SSE, and then it will kind of drop, right? Okay, what's now a good clustering solution to settle on? Well, you can typically look for the elbow point, right, that you get there, and basically settle on your K that way. It's very sensitive to outliers, noisy data, so you will need to treat them beforehand. Normalization probably required in 99 out of 100 cases. And you get blobby clusters at the end, right? Based on how that assignment works, you're looking for, well, blobby, I mean, it depends, of course, a bit on the distance metric that you utilize, right? In the case where, typically the default setting where you use Euclidean distance, well, in that case, if you look at the left-hand side, no wonder then that you get kind of a blobby outcome that might not be the thing that you expect. So some cases, maybe switching to a different distance metric might be helpful, but in this setting, it might be hard to come up with a distance metric between a center and points that would basically be able to say, okay, if you place your centroid somewhere over here, that then these points are not near to that centroid, but all of these points are near to that centroid. Yeah, then you can almost come into the realm of trying to apply some kernel-based tricks from the SVM world and maybe first transform your data in a stretched 3-dimensional space where that might work, but that's a whole other kind of can of worms that you would be opening. So typically with the standard distance metrics on this kind of irregular non-convex shapes like these, k-means will give you blobby clusters. But that's not because k-means has really a fundamental limitation. It's more the distance metric that has the limitation there. Also, because of that local optimization, well, this is a failure case where this is stable, right? None of the centroids will move anymore. So this has converged, but it's not an optimal solution, obviously, right? The optimal would be that I have a centroid here, and a centroid there. So just restart a couple of times. At least that's pretty easy to fix. Elbow points, you can do that visually or use a package such as Neat to spot that. If you're not sure how many clusters that you need, you can utilize this. Now this reveals something, and that's another thing why people oftentimes don't like k-means in practical cases. One is because, yeah, the distance metric, if you don't get creative with that, your clusters might be too circular in shape. The other comes from a typical use case where you have seen in class, okay, I need to apply k-means and I can use that for customer segmentation. Okay, so I've already, or to make the example work, what was done here, the original data, so these are all customers, has more than 2 features, but for the sake of visualization, they are dimensionality reduced. We only show the 2 principal components there, and we show the clustering solution on top of those. And it might be that you already have some outcome in mind. You might already have like your bronze, silver, gold customers from a previous marketing campaign, or that's typically what you expect to see. You might say, okay, at the end, I have my customers here and I would like to get 3 groups, right? Because that's what marketing likes to work with. So I want to look for these 3 groups that are present in my customer base. Okay, so you run your k-means with, and you set k equal to 3. And then you go inspect those clusters and you go, oh my God, what has happened here? Like this, whatever this then is, bronze, I guess, customer group, or it's basically a mix. But this group of customers, and you would start to inspect them, basically doesn't show you to be a very coherent group. And when we say inspect, a cluster, again, with 2 dimensions, like here, that might sound easy, but originally you had more than 2 dimensions. So what do you typically do is you expect the centroids per cluster over your features that you have, or you make a histogram in 3 different colors in this case over the features to see where the differences are between each of those 3 clusters. What you can also do is, now that you have your 3 cluster labels, use those as a target, a multi-class target, and run a decision tree that can help you to explain where the differences lie in these 3 clusters, right? So again, in the 2-dimensional case, this is always easy, but if you have more than 2 features, you need to do something on top of that. So you run a decision tree, and for that first cluster, you see that it generates a lot of leaf nodes. There isn't a very coherent explanation. So the histogram looks pretty mixed as well. So what has happened there, right? Not a very good solution. Well, it's not because you have 3 final clusters in mind that you want to construct, that 3 is the optimal value for k-means, right? Think back of that SSE story that we had, think back of that convexity story that we had, even although here, all of the groups that we had, they are kind of nice, blobby shaped, right? But of course, 3 clusters will not be sufficient to capture kind of the different groups that we have here well enough, right? You might, and typically the way how these segments are done, they're based on some sort of customer lifetime value, but you also have other features in there that might also cause your customer mini groups that you have there to differ a lot from one another. So very often in those cases, for segmentation purposes, the kind of takeaway tip is start with a higher number of clusters than the ones that you actually want to obtain at the end, driven by your domain goal or whatever that it is. And start with a higher number, which pushes that SSE down a little bit further. And that will help you to then inspect, in this case, these 5 clusters in a better manner, because now the explanations that you get for these 5 clusters will be, of course, more easier to inspect. Your decision tree, if you now build this on top of these 5 cluster labels, will need to become less deep and will have a clear rule to identify whether someone belongs in cluster 1, 2, 3, 4, 5. And then you have 2 choices, right? Either then you say, actually, now looking at this, we need to group or we need to label these 5 clusters with 5 clusters. You can then give them a name and you continue to use those. Or you can say, okay, I now understand why this group and this group are indeed different, but for my purpose, I will still merge them and consider them to be called the same name anyway, right? Because for the features that matter to me, those are the ones that I will utilize, but then still knowing that, okay, within this group that I just called before my bronze customers, I am aware of the fact that there are actually 2 very distinct subgroups in there that I've called the same, but behave perhaps differently. So don't be afraid to set this k-value higher. You still have the choice to manually go in and merge afterwards. And that's what you see a lot with these unsupervised techniques in general, that out of the box you're sometimes disappointed with how they work because they require a lot of post hoc filtering, analysis, merging, and so on to make them work. What does k-means plus plus then do on top of k-means? Well, we just saw that this initialization is a bit of a weak point, where you start with your initial centroids is a quite important piece in terms of where you end up, either in a local minimum or in a global one. So maybe we can improve that a little bit. And what k-means plus plus does, it says, well, make the picking of those initial centroids a little bit smarter. And when you pick your first centroid, you just close your eyes and you do that completely randomly. But then for your second centroid, well, we can kind of draw some kind of distribution around this first one, and we say, okay, to place your second centroid, do not do that completely random anymore, but weight that in some sense, so that it's less probable that you will pick a centroid which is close to one that you already have, and more probable to pick a space which is further away, right? Not completely impossible, just more probable that you pick a space which is further away. And then for your third centroid, same thing, more probable that you pick a position which is further away from the 2 existing centroids that you already have. And that small trick already helps to make k-means behave better. Very often, most implementations, even though they call it k-means, they will just use this instead. They will implement this already. And they will also do multiple restarts. So if you look at scikit-learn, for instance, in the docs, you will find that that's exactly what it does. Now you might say, okay, something so boring as k-means still has a bit of issues. And one of the issues is that I just told you, well, you could implement this with stochastic gradient descent. You might be wondering about, that means that I could code this up in PyTorch and I could switch my device to CUDA and then I can run k-means on the GPU. And instead you could, indeed you could. There is one tricky part, of course, in there that, okay, there is some assignment step that needs to happen there that you need to implement, which means that you need to calculate the distances between those centroids and all of the instances that you have. And if you then look at if the number of instances increases and the number of clusters as well, yeah, probably there is a lot of data movement that needs to happen there in that case. So, and typically GPUs like to operate on a whole bunch of data as much as possible. So this kind of assignment step will not be that scalable. So just to say that also in this realm of k-means, there is still new things that happen. A couple of weeks ago, something called flash k-means was proposed, which try to take k-means, have that run on a GPU, but where they optimize its internals, because it's bottlenecked by the theoretical algorithmic complexity, to remove those bottlenecks. And basically where they remove that assignment step with something that they called flash assign, which fuses distance computation with an online org-min to bypass intermediate memory materialization, which is a fancy way to say bypass the fact that you need to iterate over all those instances that you have. So interesting to, or it's nice to see that even for something like k-means, once you go to the realm of not having 10,000 instances, but billions of them, this stuff becomes important, obviously. Now, there is another kind of partitional clustering technique, not hierarchical, that we can look at, and is also very commonly utilized nowadays, and it's become more popular than k-means by far, which is called dbScan. And dbScan is an acronym for density-based spatial clustering of applications with noise, a whole mouthful. There is also a hierarchical dbScan that was released afterwards, which is also very popular, but we focus here on the base version to kind of introduce how it works. The nice thing about this is it doesn't even ask you upfront how many clusters that you want to get. So yeah, that's not a decision that you get to make anymore, but instead you have some other hyperparameters to play with in terms of minimum points and distance, that epsilon that you see there. And another nice thing is that, first of all, it's not kind of limited to these, convex-looking shapes. It will basically be able to do this sort of thing pretty well. And in the figure where we compare the different clustering techniques, dbScan was number 3, for instance, so the one that you guys like most. And on top of that, not only is it capable to identify those kind of clusters pretty well, but it's also capable to identify noise as well. So if you do have outliers in there, it's quite likely that dbScan will say, oh, look, I refuse to cluster those or put those into a cluster. I will just call those noisy labels instead. Later, you can override it. If you still say, nah, I want to make them part of a cluster, you could still step in with some sort of distance metric in that case and make them part of a cluster, right? Why not? That's still something that you could do. How does it work? Well, it's actually relatively simple. It starts with randomly picking what will then become a core point, quite likely. So it randomly picks an instance which is so far unclustered to start from. And then it looks in a radius with a distance epsilon to kind of see, okay, can I continue to grow this thing further out? And there are two cases that can happen there. Either you have not sufficient minimum points in your neighborhood to basically say, okay, you're a core point, right? Or you have, in this case, even 0 points in your epsilon radius, in which case you will be labeled a noisy point, and we just continue with the next one. In the case of a core point, if I look at its radius there, I do see that I have 1, 2, 3, and myself points in there, so I can be considered a core point. I then label all of my neighbors in that radius, which are these guys, and say, okay, the next step is I will also check these 3, and I will grow, basically, I will spread the infection, if you will, a bit further on. And for this guy, I do the same thing. I check its neighborhood, and I see if I have sufficient points in the neighborhood, and as long as I do have sufficient points, I will continue to spread the infection. And it grows out over time, like a mold or a virus, until you end up with one of these yellow cases, for instance, was selected based on this one, had enough points in its neighborhood, so this one got selected. But when I look in that one's neighborhood, I do not have sufficient points anymore, so I will not spread the infection further from those guys, and those become my border points. And I continue to spread until I end up with only border points remaining, and then I stop. If I select one again to start from and I do not have sufficient points to begin with, then immediately that becomes a noisy point and nothing happens further. I simply select the next one to work with. And that's a very, well, simplistic algorithm, but it works quite well on all sorts of data. So let's say we have our smiley face over here. So the two parameters are the epsilon, the radius, and the other parameter is the minimum points that I want to include. So let's set that to its defaults, right? And I start something like this. Start from a random point, I spread my infection, and at some point you will see that this will stop. And in the ideal case, it will be capable to identify the full outline of the smiley face as one cluster, right? But that doesn't necessarily always happen. Like I think there, yeah, so there a border point has been reached, but the other side still continues. So it's almost finished building that first cluster. Yeah, even succeeds. Then the next one, then the next one, and then the final one. And in this case, very likely, there will be no noisy points that it identifies. So what happens if you change a bit with, or if you modify these parameters a bit? Let me say, okay, same one. And now I say, okay, I make the radius way smaller, right? Well, you can kind of imagine what's going to happen. Way more clusters will be built and more points probably will also be identified as noisy points. Drawback here, of course, is that these parameters, these defaults, if you have normalized your data somewhat, yeah, they will work quite well, but changing it can have a large effect on your clustering outcome. There is another drawback as well in the sense that this, if you would like to implement this in a predictive pipeline, tomorrow I give you a new unseen test point, and you need to tell me what is the cluster that it belongs to. With k-means, at least you can not touch your centroids anymore. You just calculate the distance to your centroids, and you say, okay, I'm going to assign you to the centroids that you're closest to. In this case, if I now give you a new point, what should I cluster you as? I'm not going to rerun dbScan because I will completely change my clustering solution, potentially. So probably there you would have to stick to also using some distance to try to squeeze that new point into the existing clustering solution. So be a bit careful. Again, train split versus test split if you want to use a clustering technique in that sense, that you do that correctly and not always rerun your full clustering. But dbScan is extremely extremely often used nowadays. And then you have others, like this is an interesting one because you could wonder, why does k-means need to be so harsh in its assignment step? You always belong to exactly one cluster, but let's say that you're a point, and k-means does not identify noisy points, dbScan does, but you could say, okay, even in the case of k-means, if you do have points and the distance to two centroids is more or less the same, then it might still be better to say, well, you belong for 50% to that cluster and for 50% to that other cluster. Why should it be a winner-takes-all mentality? Okay, we can try to set it up, and we can also try to train that, in which case that, again, we're trying to position distributions, if you will, in our feature space. So we're trying to optimize a mixture of Gaussians, for instance, and we can use expectation maximization to do that, and then you end up with a solution that looks something like this. But you could also say, well, I'm just going to let k-means run, but then for the interpretation step, I will look at the distances, not just to the closest centroid, but to all of the centroids. And if I see that your distance is very similar to centroid 1 and centroid 2, I can also still say that you belong for 50% to cluster 1 and cluster 2, right? And if you think back about what our variational autoencoder was doing last time, it also links a bit back to this story as well, right? Positioning of distributions and so on. So this is also local optimization. We try to now fit Gaussians in our data space, but yeah, it's not oftentimes used because it has the same issue with non-convex shapes and so on. And basically, you can just use k-means and do the assignment in a less hard version as well. Mean shift clustering then builds on top of kernel density estimation and does something similar. It says, okay, again, in the two-dimensional case, it's pretty easy to see, but we place a kernel around every point in our data set, and the kernel here is not the same as the filter that we had in our convolutional neural networks, but kernel coming from kind of the similar aspect as support vector machines, a weighting function that we apply on all of our instances. And in this case, what we could pick is, of course, a Gaussian kernel, like always, meaning that around every instance, I basically put a Gaussian on top of that. And I sum all of these Gaussians together, so basically I will end up with a landscape that looks something like that. Or viewed from the top, I get a contour map that looks like this. And then to cluster, what I will do is I will basically take all of my instances, and instead of gradient descent, here I will basically do gradient ascent. In every step, I will basically climb up the hill and climb up my closest hill. And meaning that this group of points, they will obviously all climb up this hill. This group of points, they will all climb up this hill. And this group of points, they will all climb up this hill. I continue to do that until my points don't move a lot anymore. And then I can just say, well, all of the guys that ended up close to one another on this hill, they're probably part of the same cluster. Also an iterative approach, also pretty easy to understand. Some cases also has some nice benefits because, of course, here the interesting thing is, okay, what happens if I switch from using a Gaussian to another type of kernel that I could apply, right? And also in the case of these examples that we saw with the non-convex case, with those two half moons, that will also work better if you use something like mean shift clustering, because then everybody will climb on the hill that belongs to their half moon rather than having some global centroid that then maybe takes in instances that you do not want to take in. So also this one tends to be utilized from time to time because it does also nice benefits. And basically what this ends up doing with the case that I described before on the half moon data set, where I said, well, if we could apply some sort of kernel where we stretch this thing out in three-dimensional space so that it becomes clear that all of these points actually belong together, and with a normal support vector machine that could then help you to linearly separate those cases, well, in this case, what it helps us to do, you can imagine for my half points that my two hills that I get, well, I'm getting exactly that kernel effect. And now the half moons both climb to the top of their hill, and I also get that same effect. So that's the, if you visit the website, there is the animation there, but I think the point is pretty clear. Now, one thing to end the clustering aspect is how do you validate a clustering solution? Well, we already saw a potential case. We could calculate that as a z to the centroid for all of the clusters, and the lower, the better. But of course, it's extremely subjective, right? Because yeah, if you use the same function to evaluate your clustering solution than the one that you use to optimize for, at the end, you will basically say if you put everybody in their own cluster, you get a very low SSE, so that's probably not what you want to look for. So potentially, you would also look for metrics that maybe say, okay, we want to contrast that in some way with the number of clusters that you also have built, and the more clusters that you build in evaluation, we also want to punish you on that somehow. So you have metrics available like the Davis Boolean index and the silhouette score and so on. But important to take away is that best is to inspect your clustering solution. And since this is so descriptive in nature, and very often you have metrics that then try to compare a certain clustering solution, like in benchmarks, with a known ground truth. But even if you do end up with a clustering solution that deviates from that known ground truth, who is to say that that clustering solution is also in some sense not a good one? There can be more than one potential ground truth available, right? So again, my advice would be either you take this as a descriptive thing, and then best is that you get to work with it, or if you do plan to implement this as something larger in a predictive pipeline, then it's your supervised score, your metric like your AUC, that will tell you whether it was a good idea to use clustering somewhere in your pipeline overall, or it wasn't a good idea, and you still rely on that supervised evaluation instead. Yeah, applications I already mentioned, like marketing analyses, but we also saw in interpretability that we created super pixels or groups of pixels. Same there. To do this, typically k-means is utilized. Also to extract like the major colors from an image, you can also apply clustering. When we apply it later on social networks, we will see that we can utilize it to detect communities of people. And there are other cases like this as well. You can think about spatial use cases where your clustering is primarily driven by coordinates, right, by location rather than features, and so your distance metric might need to be redefined a little bit in that case. So there are lots of cases where it shows up, but very often mixed with a predictive thing or maybe something more descriptive oriented. And what's also nice is that for some cases you can even put in a bit of domain knowledge where you say, well, I do know that I have two instances that do need to belong together. Even although they might be, or they might look far away in feature space, I do want to make them part of the same cluster, and you never break up that relationship. Or maybe there are two instances which you can never put in the same cluster. And then if you think about how you would implement agglomerative clustering, for instance, these domain constraints are, I should say, relatively easy to implement. It becomes harder, of course, if you really go overboard and you start to give the algorithm things that it can never match, right? If I say that person A, B, and C must all be in the same cluster, but B and C cannot be in the same cluster, well, that will obviously not work, right? So, and also for distance metrics, if you would work with textual instances, look for an appropriate distance metric. If you see that you have a very high dimensional numerical vector, use cosine distance. If you have text, use Levenshtein or the edit distance. If you have images, use the perceptual distance. If your vector is binary numbers, all 0 and 1s, use Jacquard, for instance. If you have a mix of both categorical and numerical features, look at things such as the Gower distance, which is a better distance metric when you have both categorical and numerical data types together in a single feature vector. So I know that very often you just stick to fine Euclidean or whatever, but there lies, I mean, the main thing that you can tweak here are those similarity metrics. For the rest, once you have that, clustering is not so difficult, obviously. Okay, good. That brings us then to dimensionality reduction, but let us first go for our 10-minute break. Okay, good. So onwards to dimensionality reduction, also unsupervised, different type of pattern. We want to find a less dimensional representation that retains as much of the something that was present in the original feature space. And there, of course, the most well-known case is principal component analysis, or PCA, which you could say, well, or not you could say, which tries to retain as much of the variance that you had in your original feature space. The typical kind of example here is that you, for instance, have an original data set which consists of 3 features. What you try to do is you try to find if you need to reduce that to 2 principal components, so to the 2 features where the first one explains the largest variance, the second one adds in a bit more variance, and so on. Of course, if you again take the 3 principal components, you again have your original feature space, but just retransformed, or linear transformation that repositions that. But if I take the original 2 ones, you could say, okay, I am in this 3-dimensional space in that case, and I'm a camera operator, and I try to position myself with my camera vantage point so that on my viewport that I get, the things that were most dissimilar to one another in my original feature space still look dissimilar to one another in the reduced feature space. Obviously, you could also say that I could take a horrible positioning and I look at my data set coming from over here, where some things would start to overlap with one another, and I lose that variance that I have there. So your PCA transformation is then a linear transformation over your original feature space. That's well known, still gets widely applied. We'll talk about some other kind of perspectives on the problem of dimensionality reduction instead. What you could say, and that's basically where we can start from, is, okay, if you look at what does it mean to reduce variance, or to retain variance rather, in the case of PCA, you're basically saying, okay, for me, it is important, given the dimensions that I retain, the dimensions that I do have or want to keep or construct, that things that were far away from one another in my original feature space, that I still see those as being far away from one another in my reduced feature space, right? So that's clear to see. PCA puts a heavy emphasis on, for instance, that red group of instances and that blue group of instances. The distance between them is large in my original feature space, so I want to retain that variance, that large distance in my reduced feature space. And if I do need to make sacrifices, then probably in the case of PCA, the sacrifices will be at the level of, well, if things are already close to one another in your original feature space, then that's a variance that we don't need to care about, because anyway, these were already close to one another. If we bring them even a bit closer to one another in the reduced feature space, well, so what, right? Now, what if we change that around? What if we say, but wait a second, what if my positioning would be things that are nearby to each other in my original feature space, I want to keep those nearby in my reduced feature space. And for things that are far away from one another in my original feature space, I don't really care so much that you bring those a bit closer. So I care more about local similarities rather than kind of the global picture that retains me that variance. Wouldn't that also work? And that's exactly the strategy that something like t-SNE aims for. t-SNE and, in the same family of dimensionality reduction techniques, dimensionality reduction techniques which are so-called manifold learners. Manifold learners, that's a whole kind of story that we need to construct there. It's kind of an area in mathematics which is quite daunting, but we will take a look at what that means. So t-SNE has a nice couple of properties. It's nonlinear, so that's already something that you could say it as a difference to PCA. It's a manifold learner, and also we will see that it focuses on retaining nearby distances. So locally surrounding instances, keep those close to one another, but if two things are already far away in the original feature space, we don't really care about where we position them in the reduced feature space. And the way how this works, if we say that this is a manifold learner, well, the assumption here is that the data points that we have lie on, this is a whole mouthful, embedded nonlinear manifold within that higher dimensional space. And a manifold is a topological space that if you look locally in that manifold, in that reduced topology with a reduced number of dimensions, where if you look locally on a small enough scale where it behaves as if it would be a normal Euclidean space, so your Euclidean distances still work correctly or comparable if you would take them in the original feature space versus the reduced feature space where you construct that manifold, where those distances, as long as you stay nearby enough or close enough or zoomed in enough, that Euclidean sense still works, but not necessarily for cases that are far away from each other, which is exactly what we want. We will reduce in such a way where if we look nearby an instance, there things that are Euclidean locally nearby need to continue to be behaving in the same way, but if we look further away, we don't really care. Example, and I'm gonna do my best, I always try this, but my drawing skills are not that fantastic, and especially because I need to go from the three-dimensional case to the two-dimensional case, because if I would try to do it from 2 to 1 dimensions, the example doesn't really work that well. So let's see, I have something which, I have an original 3-dimensional space, and let's say my data behaves like some U-curve shaped, right? So I have some points, so I'm kind of drawing them on that axis, but then I go downwards. And now I'm flattening out my U-curve. And now I'm increasing on the y-axis again. And I know the perspective is already a bit messed up, but that's kind of the shape that I have. So if I would try to draw an outline, kind of this kind of shell U-curve based thing that I have here in my 3-dimensional space. And what t-SNE will aim to do, or what it means to construct a manifold, and we actually already saw it in the GAN example as well, but then I told you not to care so much about it. But what it means to construct a manifold is, well, exactly the shape that I have already drawn. I could say, well, what if I say all of these points, I want to get rid of one of the dimensions here. So I will give you a new 2-dimensional piece of paper that you need to place these points on. That's basically the same thing as what I did with PCA. I said, okay, I give you a new viewport, a new piece of paper, 2 dimensions, and you need to project these points on these 2 dimensions. And with PCA, we said, well, I'm going to take a projection, right? So there it's a linear transformation in such a way that these long distances that I have over here, I need to continue to see them in my first principal component. So there your projection will probably be something like this, where your points end up structured like this, because this variance that you have there then gets nicely retained in your reduced feature space. Not so much for t-SNE. t-SNE says, well, if you give me that two-dimensional sheet of paper, that's my manifold. And I'm going to try to place that manifold in that original feature space, so that allows me to take that piece of paper and to wrinkle it, right? To slide it around, to play with it, to basically move that sheet of paper like I want it to. So in this case, what I would do to best fit those three-dimensional points that I have and project them, I would probably exactly take that piece of paper, kind of bend it like this, and lay it out like that in my original three-dimensional feature space. And then I can basically project all of my points to that two-dimensional space that I have, and then I have the new positions. And then I take that piece of paper, and I basically unwrap it again, and I place it over there. Now, what you would see in that case is, and here, again, it's for the sake of illustration. We will see a bit more extreme cases, but this is the simplest thing that I can draw. If I then look at distances between instances that were close to one another in the original 3 dimensions, and I would then calculate the distance over that manifold that I have projected them on, that they stay pretty close to one another. The distances weren't disturbed too much, right? Well, different to if I then take an instance over here versus an instance over here, I can calculate the Euclidean distance between these two instances, but if I then try to do the same thing following the manifold, the distance might have become way larger, the distance might have become smaller, that Euclidean metric breaks down, right? Because I've basically tried to position a piece of paper and wiggled it around in my 3-dimensional space, so things that were originally far away from one another, who knows where they ended up. That means that you can end up with cases where your 2-dimensional reduction of something like this, and that's why we need to be a bit careful when inspecting dimensionality reduction techniques that stem from manifold learners. I'm not saying that they can't be useful, quite the opposite from that, but where you will see, for instance, like the typical snake-like pattern, and you get this as your dimensionality reduced solution. And your original data, your data didn't follow like a snake-like pattern at all, like this, so what happened here? Well, basically, same thing. For things that you see which are close to one another in this reduced feature space, the thing that you can say is, okay, these are cases that were close to one another in the original. But what happens between here and here and here and here, that has more to do with the layout trying to make optimal use of the manifold that it has been given, rather than trying to retain that variance or those long distance metrics. So be careful to make assumptions in the case of, well, these are the 2 furthest away points, so it means that these are the most dissimilar. No, that's something with PCA that you can do, not in this case. But you can say, okay, if I look locally, the structures that I see there, these instances belong together. And I've just unrolled them or packed them in that manifold as well as I could. How, though? How do I then find this projection from my original 3-dimensional space to my 2-dimensional space? Well, we'll work in 2 steps. Step 1 is I will construct a probability distribution representing similarity over pairs in my high-dimensional space. So my 100 dimensions that I have, or, and we will see, this is something that makes this work quite effectively, is even something so high-dimensional as an image, where you have width times height times red, green, blue, and you just use that as numerical features, right? So that's already easily thousands of features, right? If your image is large enough. And you just run t-SNE on top of that, and you reduce that to even 2 dimensions, that your images are laid out pretty nicely, right? That there are groups that appear in there. So that's typical a benefit of these manifold learners, is that they're capable to find these structures in way higher dimensional data than PCA typically can do. So that's where they oftentimes show up. We will also, in our low-dimensional map, we will also construct a similar probability distribution. So I have a probability distribution that measures similarity between pairs in my original feature space, and then in my low-dimensional space. So that means that I do need to have a candidate solution where I say, okay, for every instance, I will place you somewhere to start off with. Here, 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 and here. That's my initial configuration. I will calculate a probability distribution in here, and I will compare that with a probability distribution in my original feature space. And I want to make those similar as much as possible. We already saw something that can help us there, KL divergence or JS divergence, as we saw previously in some cases. I'm trying to make two distributions as similar to each other as possible. And here, the important thing to realize is that this works even although the dimensionality between the original feature space and the reduced feature space is different, because the probability distribution here is expressed over the number of pairs of instances that I have, rather than something which is expressed over the original dimensionality that I have. So that's a bit dissimilar to when we were talking about our GAN story and so on. So here my distribution is expressed over my list of pairs of instances. How similar are these to one another? Meaning that I will construct a list, okay, for every pair, so number 1 and number 2, and number 1 and number 3, and so on. How similar are these to one another? And I will do the same in my original 3-dimensional featured space. Same thing for pair 1 and 2, 1 and 3, 1 and 4, and so on. How similar are these? And I want to make this thing as close as possible to this thing. That's the idea. How? Well, in step 1, I need something that then again can say, okay, for every pair that I have, I need to hence measure some sort of similarity. So a whole bunch of tricks gets opened up, but the idea itself is relatively simple. So what we introduce here is, if I need to calculate the similarity of an instance xj, how similar is xj to xi? And Teasney introduces something that it calls conditional probability, called pj given I. And this expresses a probability that xi would pick xj as its neighbor if the neighbors were picked in proportion to their probability density, assuming a Gaussian kernel centered around xi. And we do that for all the other points. So basically this whole nasty thing that gets introduced here, we will immediately see we basically fit a Gaussian, and the bottom part here is just to normalize this. So the top view is basically the view that we need to keep in mind. But problem, this means that I have something which is not yet unordered, that I might end up, if I calculate p j given I, and I calculate p I given j, that how similar is 2 to 1 versus how similar is 1 to 2, that I might end up with two different values there. And we just saw, yeah, but for a similarity metric, it's nice that you have symmetry. If I ask the similarity between y and j and I, that's similar, that's the same. Okay, no problem, then you also introduce a pij on that, and you just sum both of them together, divided by 2 times the number of dimensions that you have. And here, because we work with a toy example, we start with 2 dimensions. Reducing 2 dimensions to 1, it doesn't make a lot of sense, but it's just so that the visual is a bit easier to understand. So let's say we have 3 data points, xi, xj, and xk here in my original feature space that I want to highlight or kind of illustrate how this works. And we force that the self-similarity pii, we set that to 0. So we say, okay, if you want to know the similarity between you and yourself, that's 0, right? So we also enforce that. So what this basically means is, okay, how likely is it that xi will pick xj as its neighbor? How likely is it that xi will pick xk as its neighbor? Easy, yeah? Take your original dimensional space, and again, put a bubble around it, plot a Gaussian around it, like we did so many times when we were talking about kernels and so on, and in lots of other cases. So in the 1-dimensional case, again, that would mean put a distribution around it. And again, we saw that in our variational autoencoders, same thing here. We're basically putting a distribution around every data point. We're placing a kernel on top of this. Once we have that, basically that kernel will tell me, okay, the more that an instance is in the yellow zone around xi, the more probable it is that you will be picked. And the further away that you move from that yellow zone, you go to the dark blue, the more improbable It never becomes exactly 0, right? But it gets very close to 0. So we can calculate that. We can say, well, the probability that I would pick J is 0.78 divided by that normalization term that we have at the bottom there, that we just call Z for the sake of keeping it easy. And the probability that it would pick K is already less, right? It's only 60%. And then we need to calculate that denominator, so we are normalized against all the points except xi itself, so that's where the sum says over all the points except for yourself, you calculate that whole thing again, that's what we divide by to basically normalize. Make sure that all of these pairs that we have, that sums nicely to 1, right? That's what we want to do there. Okay, and then we do it in the opposite direction as well to calculate the Pij that we have there at the top. Key choice here is obviously, like it is as always, whenever you introduce a kernel method, right, the same stories come back, no matter which algorithm that you utilize. It's actually quite fun. Like you have SVM, so you need to put a kernel, radial bandwidth kernel. Okay, you put Gaussians on top of your instances. How large do we make the bandwidth, right? How much do I spread out this Gaussian? Do I make that a very skewed, or no, skinny, I should say, Gaussian, right? Something that looks more like this, and you're only my neighbor if you're very close to me, but otherwise not? Or do I go for something very wide like this, where I consider a large neighborhood? Well, depend a bit on the density of your data, on how, whether you normalized your data and so on. You can play with that. And to make it even more tricky, instead of saying, we pick a global bandwidth, which is that sigma basically, right? So that deviation that basically, or that covariance matrix that basically influences our bandwidth. Instead of picking a singular one for all of these guys, another issue is we have different data densities. Also, the density of our data is not the same everywhere. If I look at this outer circle, my neighbors are a little bit further away from me. If I look at that inner circle, my neighbors are closer to me. So my density across my data might also change. So what if I pick a bandwidth per instance? And the Gaussian that I draw around every instance can be of a different bandwidth. So now the bandwidth is instance dependent. Right? And you might say, oh God, that means if I have 1 million instances, I need to pick 1 million bandwidths, right? So I will still make them all the same in that case. So of course, that's not what you will be asked. The idea is that you will still be able to set a singular parameter, but then under the hood, this will translate to different bandwidths depending on in which kind of density that we are in our data set. But that's the idea. So we can calculate then the joint probability. We do Pij and Pik and so on. So we know that I and j, now we have a single distance metric, and no matter if I do Pij or Pji, this will be 0.0069. So these are more similar than Pik. And that's how I fill up my whole table on the left-hand side. Oof, okay, now I have that for my original feature space. So it's based on Euclidean distance using that bandwidth. It's data point dependent. In practice, however, the single measure that you can tune is a parameter called perplexity. It's a measure to estimate how well that a distribution predicts a certain sample. So you basically set a single perplexity parameter, and then that gets translated to these individual bandwidth parameters per instance. So the bandwidth parameter is adapted to the density of the data. Smaller values are used in denser parts of the data space, which makes sense. If you're in a space of your data where everybody's close to each other, you will make your Gaussian skinnier than where everybody's far away from one another. So that's something that happens there under the hood. Okay, fine. So there we use a standard Gaussian distribution, fine, similar to other bandwidth methods like in geographically weighted regression. There something very similarly is done where also you have an instance-dependent bandwidth, because also there you make Gaussians on points that are have coordinates, so are spatially distributed, but also there the densities might differ, so you might need different bandwidths per data point. So you also start from a single parameter and then you try to estimate the bandwidths in an instance-dependent or specific manner. So that perplexity is something that you can play with, right? That you can control. That's for our original feature space. Now we do the same thing. Okay, we have a suggested position for all of these original points in my reduced feature space or my low dimensional space. So also there we do the exact same thing. Instead of calling it Pij, let's call it Qij. So you don't have to, but to make it a bit more fancy, instead of saying, well, we use the Gaussian distribution, in the low-dimensional space, we'll use the student T distribution. Why? Because that thing has feather tails, because you work in a lower dimensional space. We know if, in those cases, if you have less degrees of freedom, that student T is a little bit more robust. That's a choice that they made. It doesn't matter that much. Whether you put a Gaussian or a student T distribution in there, basically you construct the exact same table for every pair of instances, a similarity metric in exactly the same way. And again, same assumption that also in your low dimensional space, you're completely similar to yourself, right? No matter where I put you in that lower dimensional space, you're also similar. And also in my low dimensional space, I don't need to set a perplexity parameter. Why not? Because in my low dimensional space, well, there I can assume that at least I will position you in such a way that I do not have sudden shifts in terms of data density, right? I have that space in my manifold to play with, so I can, if I would see that, for instance, here I have more instances, right? And I could stretch out my manifold a little bit here, right? So that in my reduced dimensions, that kind of the average distance between instances is generally the same, right? So that there, if I put that Gaussian on top, basically there I do not want to have sudden density shifts anymore. So there at least I get rid of that perplexity parameter. So I have that whole table of similarities between I and j, right? Except I with itself and so on. And I need to, again, now check how similar are these two probability distributions. So you stick something like a KL on top of that, or a JS on top of that. In this case, standard, a KL divergence. And then you say, okay, fine, that's the thing that we need to optimize. The table on the right-hand side needs to become as similar as possible as the table on the left-hand side. Optimized using stochastic gradient descent. Why? These are my weights. These are the parameters that I can determine. For every data point, I basically need to find a position, two-dimensional, in my reduced feature space, and I will move these around. And I will move those around so that this loss, the KL difference between this and this, gradually decreases. So over 100 iterations, 1,000 iterations, until I find a positioning for these points in 2 dimensions, which retains or which has constructed a manifold in the sense that small distances are well preserved. So this is, for instance, what you get with images. Typically, if you just give the raw data, you will see that kind of it positions or it places white or very bright images close to each other, and more black ones over here. But in some cases, or in quite some cases, you will also find structure in there as well, where dresses are quite next to each other, or objects of a different type are quite next to each other. So musea, for instance, have utilized t-SNE to make interactable 2D maps that you can scroll over, where they have scanned a whole bunch of photographs and then laid them out in an atlas like this by doing a dimensionality reduction, finding a position, a coordinate basically, for the original raw image data, and works quite well. You can use it for words as well. How? Yeah, you first need to have a numerical feature vector before you can embed them and then reduce the dimensionality with t-SNE. But once you have a vector for each word, you can also then reduce the dimensionality of those and find a position in 3-dimensional space. Important, even though many people will utilize it as this, t-SNE itself does not give you a cluster solution. It's a dimensionality reduction technique. However, nothing is stopping you from then saying, well, if I now have something that has a reduced dimensionality and only has an x and a y coordinate, I can just put k-means on top of that. And given that now this manifold behaves pretty nice and local distances are well preserved, right? And there is not the only data density differences that you see here, they are not a result of the fact. So here, for instance, the way how k-means works is, okay, all of these guys, they are close to one another in my reduced feature space, means that they are similar. Between the distance of this and this, the fact that these two clusters are more close to one another than these two clusters are, that's not something that I should read into, right? I should only look locally. But when I do then k-means on top of this, okay, then I know my groups at least, right? And I see the structure that's in there. So a little bit careful, not think of this as an immediate clustering technique, but you can apply something like a k-means. Very often, we will reduce to a 2 or a 3-dimensional space, not more. Why? There is nothing stopping us from saying, well, I want to reduce 100 dimensions to 5 dimensions. The reason is that after you go beyond the 3-dimensional case, that it becomes computationally too heavy for this stochastic gradient descent to optimize the KL divergence. So very often the reduction is done to 2 or 3 dimensions. So that's a bit of a pity that we can't do more than that, or not easily. Also, this is again non-parametric. Once I have reduced my dimensions and I have placed all of my instances, and you give me a new one, and you would ask me, hey, this new one, where in your 2-dimensional space should I put that one? I can't tell you that. I would need to rerun t-SNE from scratch, and my whole positioning will shift. So again, this makes it hard to do as a pre-processing thing in a predictive pipeline. There are, however, parametric versions available as well that also do allow you to give it a new point and map it to your lower dimensional space. So parametric versus non-parametric does matter for these dimensionality reduction cases here as well. Do you want to come up with your own construction of distance instead of following this Gaussian distribution again? Well, yeah, sure you can, as long as you have self-similarity and you can normalize to sum to 1, fine. And then you might even be able to get rid of that perplexity parameter. That's only something that's related to the fact that you use that Gaussian approach there. Typically not done, but you could. Weight initialization. We know that that's quite important. We do need to start from some position. What will we pick? Random? Very often we'll say do PCA first and use that as the initialization for t-SNE. Probably that will already help somewhat. So also those kind of tricks also get heavily or very often applied. So initialization with PCA. So yeah, deep learning session to refer back to gradient descent and so on. So this also has a learning rate that you need to configure because it does SGD defaults work quite well. Now we can also say, well, maybe there is another approach that we can take. And like I just said, every time you come up with these kind of distant things where some people tell you, we use a kernel, we place Gaussians, we play with the bandwidth to handle those different density regions. There you will be able to find or propose an alternative approach where someone tells you, no, screw those Gaussians, right? What you should do instead, for every data point, you look at the k nearest neighbors. And you use that as a measure for how dense your data is in that region, right? Because if you look at your 5 nearest neighbors and they're all close to you versus they're already a bit further away, probably that tells you something about your density of the region that you're currently in. And then you will say, yeah, but now indeed I do not need to pick a perplexity parameter, but now you're forcing me to pick a value of k. Yeah, it's one or the other, right? With Gaussians, you pick perplexity. With nearest neighbors, you pick k. So it's none of them are perfect, but sometimes one turns out to be a bit easier to implement than the other. In the case of t-SNE, it's perplexity, right? And that perplexity hence impacts the neighborhood that you consider, right? So here in the right-hand case, a point that's already of the inner circle will consider to be quite near or a neighbor of my red point. In this case, I only look very locally. So that perplexity knob is an important parameter to tune when you play with t-SNE. And the effects can be quite dramatic in the sense, and that's sometimes why you do need to be careful by running something like k-means on top of this. Here you see different outcomes where the same original data set has been reduced in dimensionality over different values of perplexity. And yeah, it's very easy to start seeing some structure in there, which is not in the original data. So again, it's local distances that matter, not kind of global structure in this case, right? So again, here what I can say is that, so this is the original data, is that indeed the orange cases, if I look locally, they're indeed nearby, but longer distances, yeah, it's a pity that they didn't put them closer to one another, but I need to be careful to say, well, I have 1, 2, 3, 4, 5, 6 clusters in there, right? So that's something that emphasizes the fact that you should try out different perplexity values. Here, that structure already becomes a bit clear. Perplexity 30 or 50 is kind of the optimal case for this. And when you set it too high, of course, well, what happens here? Now everybody becomes a neighbor of everyone suddenly, so you can just clump both of them on top of each other. Anyway, locally speaking, everybody's nearby everybody. So that's the case where you've basically done this, but made the bandwidth even way higher, So even if I pick this one and this one, oh yeah, everybody is my neighbor, right? So we put everybody on top of each other in that manifold. So perplexity is an important parameter to consider there. If the website still works, I hope it does, yeah. You can also inspect kind of to get a view of how this manifold stuff works. Like if you see ring structures such as these, like 50 points, and then I play with the perplexity a bit. So you can see that it's quite sensitive to this, right? Or maybe after a while it converges. If I go even higher, probably at some point it would start putting everything on top of each other, like here, right? If I go too low, well then my neighborhood that I consider is getting smaller and smaller, and I'm hoping that I can kind of make it collapse into something. Yeah, there we go. So this is an interesting case, right? Because this is exactly like, again, we go from 2 dimensions to 2 dimensions. So it's like I take a piece of paper, 2-dimensional, I need to overlay it with that original 2-dimensional piece of paper or points that you see in that little square there, but I can scratch and wrangle that piece of paper. So here, what has happened is that manifold has been stretched to follow that original data structure, and indeed, points that are close to one another in the original feature space, they continue to be close in the reduced feature space, right? So the manifold works, but be careful to kind of say, so there is a circle or a structure, this one and this one over there, they're very far away from each other. No, it works locally. Think of that piece of paper that you're stretching out, right? So hence why sometimes k-means can be a little bit tricky to apply, because you might start to see clusters that are not actually there, right? So that's something to remember. Okay, then, yeah, so there is packages for this, parametric versions, I already mentioned this. Now that was old hat. Now t-SNE still gets used a lot, right? And still you will find a lot of cases where people use t-SNE on top of images to kind of cluster them and explore them and so on. But there is a later implementation that follows more or less the exact same idea, but with a different trick applied to it. And that's called UMAP, Uniform Manifold Approximation and Projection for Dimension Reduction. So it also uses this kind of manifold structure. But it performs way better when your target dimensionality is higher than 3. So this has the computational benefit. It has a whole bunch of other nice additions as well, in the sense that you can even do your dimensionality reduction in a more supervised setup, where if you do have labels, it will try to take those labels into account to construct the reduced mapping of your original data. So that's also nice, because very often you might already have some labels available, like if you work with images, you know the category that every image belongs to. It's parametric by default, so if you have new instances, you can also embed them, place them, position them in your reduced dimensional space. Now, how does that one work? Well, the idea is there is a whole, if you read the webpage of UMAP, they will start talking about like certain types of geometric algebra and Riemann stuff and so on. It's actually pretty simple if you look under the hood. And what it changes up is, well, effectively 2 things. It says, okay, we have an issue where, of course, this thing scales rather badly if the number of pairs grows heavily, right? It's also the fact that we need to calculate this distance and put these Gaussians, and we have all these pairwise comparisons that we need to run and keep track of. And especially then here also, if we go in the multi-dimensional case, then this dimensionality grows and so on, and will also make this, this difference harder to calculate. So that's basically the issue of t-SNE. Like when we increase the number of instances and we increase the target dimensionality, this tends to grow in ways that we don't really like. But maybe there is a way to change that. And the kind of insight that UMAP goes for is to say, well, you know what? In your original feature space, rather than putting Gaussians on top of everything, let's connect you, and now comes the alternative trick, based on your k nearest neighbors. Again, Euclidean-wise. So those are your 3 nearest neighbors, and we connect these guys to their 3 nearest neighbors, and I need to be careful that I don't have more than 3 edges going out of anything. So here I already messed up, something like that. Probably like this, something like that. And I construct a graph based on this. So I connect everybody together with their 3, or 2 in this case, nearest, well, your neighbor of yourself, right? So with your 3 nearest neighbors. And then I say, well, in my reduced feature space, I can apply the same trick. No matter how many dimensions that you have, I also check for everybody there who are your 3 nearest neighbors, no matter where I position you. And I also construct a graph on the reduced end between all of my instances. Instance 1, 2, 3, instance 1, 2, 3. And then it doesn't really matter here, the dimensionality, how much that grows, because you get reduced or you get converted to a graph representation anyway. So step 1 is to move from the Gaussian approach with that perplexity parameter to just making a k nearest graph. You still need to pick k, right? And then to see how similar that these two are, well, what I can do is I take the adjacency matrix for this graph. So this is the number of instances that I have, but I can make this sparse if I want to. The diagonal is obviously 0. And for the others, and the top half I don't need. And for the others, well, I can still do that based on the distance that I have retained, right? So here these are 0.2 as a distance and so on. And I can do the same thing there. I can also make an adjacency graph over there. And now the difference that I want to reduce is not the difference between 2 distributions or probability distributions, but is how different are these 2 adjacency matrices from one another. And I want to make those closer and closer to one another by moving the points in my reduced feature space. That's the perspective that UMAP takes. So it again positions, makes a graph, tries to make the graph as similar as the original graph that you had. And it turns out to be way more effective for mappings to higher dimensions. Still though, lots of people will still reduce to 2 or 3 dimensions even when they use UMAP because, well, it's easier to look at if you have 2 or 3 dimensions. Also tends to work better. So here there are, originally this was a whole bunch of images. The images here are not shown, but they are reduced to positions in a 2-dimensional embedding space. And we use the supervised version of this. The supervised version will then add in an additional loss based on the labels that you have. That's basically what it then implements as well. And you can see if I overlay the original labels that I have images for dress, coat, sandal, shirt, and so on, that indeed the way how that these, I shouldn't say clusters, I need to be a bit careful again because it's a manifold, but the way how the layout is done here, that basically it has followed that supervised setup pretty well. But then I can start to explore, for instance, well, in the same label, I do still see like things that are pretty nearby to one another and already things that are maybe a bit further. Are these then indeed dissimilar from one another, yes or no? And there may be some points where it has still said, yeah, but sorry, this t-shirt, it looks way more similar to a normal shirt. So I'm still going to position it here instead. So works better. Generally today, you use it as a drop-in replacement instead of t-SNE. It's faster, it's better, just use that instead. Weirdly enough, a research area that has heavily adopted UMAP is in cellular biology. So there typically, or in scans of DNA, for instance, where typically when you scan a cell, you read out its genome, you have a whole expression. That's something which is extremely high dimensional because you are testing a string of DNA for particular genetic expressions that light up by coloring the cell itself or by running it through a machine or whatever. So you have an enormous amount of features. In that case, it's typically a case where you even end up with more features than you have instances, weirdly enough. Yeah, you want to visualize how 2 batches that you have here, or maybe you want to visualize, do I have different types of cells in this mix that I have tested? K-means on top of this with so many features, good luck with that, right? So very often people utilize UMAP atlases to then find structure, and maybe they already know the labels of some cells and then they want to see, okay, probably means that the others that we have scanned here are also similar to that cell. Maybe we find new groups that we didn't know about previously that we can also take a look at, okay, is this then a new type of cell or what's happening there? So yeah, for some weird reasons this has become quite popular in that area, but makes sense, right? If you work with this sort of data, that you utilize this. This is implemented as a package that works on the scikit-learn API. It's also available in R and so on as well. So a very powerful dimensionality reduction technique. If you want to visualize something and you have a solution or a kind of setup where you have a whole bunch of dimensions, UMAP can often help to project that to 2 dimensions in a way that can be more understandable than PCA can, especially for extremely high dimensional data. Okay, and then as our last topic, this anomaly detection, outlier detection, or sometimes also called novelty detection. Outlier detection, but going a bit beyond the univariate case. What makes a case anomalous? Noisy, there can be different reasons. It can be deliberate noise because someone is trying to, or is really different than your normal cases, or maybe because of some data error, but you want to spot those anomalous cases. Typically, you can try with those histograms, those distributions, maybe even something that works in the multidimensional case, like robust covariance, but drawing an ellipsoid around 2 dimensions, it's probably not going to spot really hidden anomalous cases, right? And the typical example that people give in that setting is, okay, if you would measure the height of people and their weight, and you have then 2 groups, the biological females and males, that the females, they typically tend to follow a line like this, and the males they follow a line like this. If you look at the distributions on every dimension separately, nothing that weird is going on there. That looks nicely Gaussian, this looks nicely Gaussian. If you look at the differences between males and females, you will say, there are differences there in terms of height and width, but so what? That's what we expect. So how can I uncover the case where, okay, given that you're a male and you're somewhere over here, that this makes you, in comparison with your reference group, let's say, that still makes you anomalous. So not just taking a singular feature into account, but taking all of the 3 features into account, right? And can we spot those outliers? With robust covariance, you're still going to miss a lot of those cases. You could also say, well, we could do that clustering-based. We have already seen some solutions to tackle this. You can say, well, with k-means, if I have things that are far away from their centroid, or perhaps I could look at clusters that only have a few instances, or based on that dendrogram, or with dbSCAN, I could look at those noisy instances as well. Maybe those are anomalous, right? Maybe combining this with those dimensionality reduction techniques that we already saw, right? So that is one solution. One-class SVMs is another solution where you apply a support vector machine, but without a class label, where it basically tries to fit a distribution over what looks like the normal cases, and then everybody that falls beyond that learned frontier you can consider to be anomalous, but that's heavily sensitive to the kernel that you pick. We already saw the idea of using autoencoders as well. So remember that in this story too, right? Where we said, okay, if your reconstruction error is high for a particular instance, that probably makes you a more anomalous case, right? So autoencoders are a technique that still get utilized quite often in the case of anomaly detection. But there is an even more special one, and that's kind of one of the 2 that you should remember if you want to implement kind of an anomaly viewpoint or novelty viewpoint in your pipelines, and that's the isolation forest. And it works very similar to the idea of a random forest as we saw it previously. But with a difference that now we're going to drive randomness to its utmost top. In the sense that now when we build trees and we need to decide upon a split, right? And remember, we want this to work unsupervised, so we don't have a target. But no worry, because what we will do, we'll close our eyes, and every split we'll pick a random feature, and we'll pick a random splitting point. And that's how we build up our tree, until everybody's in their own leaf node. And we build 100 such trees. Oh, wow. So completely randomized trees, right? So it's not entropy-driven anymore, not information gain-driven anymore. We basically construct completely random trees. So that's fast, easy to do, right? How can this possibly work? Well, think about it. If I have a data set. Again, 2 dimensions, like always. And I have a whole bunch of instances over here. And then I have a couple of weirdos over there. And think about I'm making splits randomly until everybody is isolated in their own little box. Randomly means I pick either this axis or this one, and I just draw a horizontal or a vertical line with my eyes closed, right? The first one, the second one, the third one, the fourth one, the sixth one, and so on. And I continue to do this. Here I will need to build quite a lot until everybody is isolated. If I would then plot this tree, and I would take the path from the top, and the number of steps that I would follow, even when I construct this randomly, before I have isolated this one, versus before I've isolated that one. In this case, the number of steps from the top to this leaf will be less. So if you're more anomalous, it will take me less random steps to isolate you, right, than for a normal-looking case. And the idea then is, okay, knowing this, I will assign you an anomaly score based on the number of steps it took to isolate you in a randomly built tree, averaged over 100 trees that I built. And that's it. Nothing more than that. So you just build random trees, you count the number of steps before you get isolated, you average over the number of trees. Easy. Can work with nonlinear data, can work with outliers, you don't need to normalize, all the same benefits that a random forest gave you, and now to find anomalous cases. So ideal case, very easy to set up. Easily train in parallel, embarrassingly so, you don't even need to look at the data, you just make trees randomly. Another one which is quite popular is again based on that KNN idea, where you say, okay, a good idea to measure how anomalous you are is to measure the density based on you and your neighbors, and compare that density with your neighbors and their neighbors. Meaning that I will pick a value for k, and I will look at your 5 nearest neighbors, and I will basically look at, okay, how far away are those neighbors of you? But that's not sufficient. If your 5 nearest neighbors are all far away from each other, well, maybe that's normal, right? Maybe that doesn't make you so weird. I could just be in a space of the data where everyone is kind of far away from each other. So what I do is, I then go to your 5 nearest neighbors, and I again ask, give me for each of those their 5 nearest neighbors. And if there the distances remain relatively stable, they remain the same as my original instance, I could say, okay, no worry, yeah, you're far away from your friends, but your friends are also far away from their friends. But if that differs a lot, and I see, okay, you're far away from your nearest neighbors, but your neighbors, they do have a whole bunch of close instances that are very nearby, or perhaps even further away than you were to your neighbors. So if the difference is large, that is what I will use as your anomaly score, right? So here, the size of the circle indicates the anomaly score, and you can see, well, here, for instance, I look at your nearest neighbors, I look at their neighbors, same density, small anomaly score. Here, it's already different, right? I look at your nearest neighbors, there's already a lot of variance there, and if I then inspect those neighbors and compare with their nearest neighbors, it's all over the place, right? So your anomaly score rises. This is called local outlier factor, a bit trickier to utilize than isolation forest. With isolation forest, there is basically no hyperparameter that you need to tune. Just build enough trees. Here, you do need to pick a value for k. That's the main parameter again, and again, it depends a bit on the data set that you're working with, but it's also a quite popular anomaly detection technique. VAEs, remember, we can also use the autoencoder with that reconstruction error to also deliver us an anomaly score as well. If you're hard to reconstruct, means you're an anomaly. So what do we do with all of these anomaly scores? Well, we can basically use it ad hoc as an unsupervised technique. But very often what you find, especially in use cases that, for instance, have to do with fraud detection, for instance, what we found is that if you, for fun, and with something like an isolation forest, remember that you're not even using the labels there, the targets that you have, but you would say, okay, what if we take that anomaly score that we get from an isolation forest, and we just make an ROC curve as if this would be a prediction? Problem, that doesn't work, because for an ROC curve, you need probabilities, and this thing gives you scores between 0 and who knows what. Yeah, make sure that it is between 0 and 1 then, right? 1 meaning more anomalous, 0 meaning not anomalous. You can make that work, right? Just take this as if it would be a predictive model. What you would find is that your ROC curve doesn't look that bad. It gets even better then if you say, hey, wait a second, if we then utilize this anomaly score as a feature to plug in a supervised model together with all of these other features that we have, and maybe one from an isolation forest, one from an autoencoder, one from local outlier factor, that this typically gives a boost in terms of your supervised setup. By adding, it depends on the use case, of course, and it doesn't mean because you're an anomaly that you're necessarily fraudulent, but typically you do see a link there. And it can also be highly powerful in those settings where people will tell you, yeah, we have a bunch of positive cases, but very little. And those are all based on the things that we used to do previously, but we're kind of interested at also spotting new kind of fraud cases. Yeah, good luck, if you work supervised. You will not find that because they're still hidden as negatives in your data. So if you throw isolation forest on top of that, you make a short list of, okay, these are the top 100 anomalous cases. You can then even cluster them or group them to visualize them a bit better in the sense of, okay, these 10 cases are anomalous because of these reasons, and or maybe you combine that with something like Shapley values, right? Again, you can take this as a prediction, and you can ask Shapley, explain to me how all the features contributed in driving the anomaly score for this one high. Still possible, right? And then from there, you can start labeling cases and say, wait a second, indeed, that's also a strange case. We should actually label that one as a positive as well. And then you have a nice loop between periodic retraining of your supervised model versus using an anomaly detection model to deliver new cases that maybe you're not spotting so far. So that's an ideal case of combining both. I, in the past, worked on cases in insurance fraud detection where we used exactly this mix. And the first cases where we worked purely supervised, it wasn't working at all. The first time that we then tried to apply isolation forest and we made that list, we used Shapley values to deliver those explanations. In the top 10 ranking of anomalous cases, already a new fraudulent case was caught that otherwise would have gone undetected. So indeed, this mix of supervised and unsupervised, in some cases, it makes sense. And also, Kate is kind of a last one that I like to introduce. It's not so common as the others are, but also to kind of switch up your brain a little bit in terms of creativity. It's called classifier adjusted density estimation for anomaly detection. So a lot of it has to do with density, obviously, right? Isolation forest measure for density, local outlier factor measure of density. And the idea is as follows. Again, you have your original data, and you say, okay, all of these, it's almost like our discriminator that we had in our GAN setup, and we say all of these, they are our real cases, normal cases. And then I'm going to generate a whole bunch of synthetic cases with numerical data that's pretty easy to do. Between my mins and my max that I observed, I can just uniformly sample synthetic cases, like a grid of them, in such a way to keep it nicely balanced, right, that I have in, the same amount of synthetic cases as I had original cases. And I will give all of them the label 1. You're synthetic. And then I train my favorite supervised model on top of this. And my favorite supervised model, as you guys know, is a random forest or XGBoost to train on this. And then, contrary to what we do normally, I then look at the mistakes that my model is making, in the sense of, where do I know that my true value is you're a real case, you're a 0, but my model is still predicting a probability which is high. And I look at those first. Those are the cases, according to my model, that look more like uniform noise rather than real data. Kind of a similar thing as that reconstruction that you try to do with the autoencoder and so on. Very simple to set up, and again works well because you can extract the power that you then have in that predictive model that you're using. the fact that it can learn, you wouldn't use logistic regression in that case, but you would use something like an XGBoost and so on. And again, you can then use something like Shapley values to give you some explanations on top of that. So that's also something that you can easily apply. Okay, next up is association rules, but do me a favor. Like I said, association rules is not commonly applied anymore. Go through these slides on your own accord. It's not that hard to understand. Have a read-through of these slides. I won't question these in detail on the exam, so don't worry about this set. It's more there as an extra. For many of you, it's also not new. If you're interested in that, you can read through it. See this as the fourth type of unsupervised pattern that you can extract. That means that then after Easter, we have room to start then with going back to deep learning and looking at textual data as our next large topic before we then move to the final one, which is graphs. All right? Have a nice Easter, work hard on the assignments, take a rest as well, enjoy the holiday, and see you in a couple of weeks.